Hi, everyone. It's late in the afternoon, so we'll try to keep everyone awake after a long day. Yeah, let's get started. Welcome to our talk. Today, we'll be talking about our insights from building some enterprise-grade machine learning experiences at Asana. So a quick introduction about us. I am Sarang. I am a machine learning data scientist at Asana. And along with me, I have Zan, who is a machine learning infrastructure engineer. So this is what our agenda for today would look like. We'll start with an introduction about Asana and some of the AI and ML themes and capabilities that we've built. We'll then deep dive into a project recommendation system that we've built and use that as a case study to dive into some key insights and learnings that we picked up along the way. Zan will then deep dive into the machine learning infrastructure and how we use or how we built our infrastructure to serve ML. So let's jump right in. Asana is a enterprise work management system that helps connect companies' missions with goals and the work needed to achieve them. Asana is powered by its unique work graph data model that connects different levels of work. So for example, you can use it to track a team or company-wide goal, where each goal is essentially connected to projects, and every project is connected to tasks that needed to be completed to achieve projects and the goals. And every task can also be part of multiple projects, and every project can be part of multiple goals, and so on and so forth. The AI and ML experiences that we build are generally built on top of this work graph data model, and it helps our models understand how work and people are connected in an organization. So the AI and ML use cases can be broadly classified into these four themes, with each theme having multiple capabilities. So for example, tasks that deal with pattern recognition, recommendations, and predictions, they generally work on structured data, and machine learning, deep learning, regular algorithms are great for working on that. LLMs are typically great at tasks related to understanding natural language, unstructured data, and the two bottom themes essentially cover those kind of tasks. In rest of our talk, we'll be mostly focusing on the first two themes, pattern recognition and recommendations and prediction, where we build machine learning, deep learning algorithms on structured data. So let's take a look at some of the machine learning experiences that we've built at Asana. We've developed smart rankings across different surfaces to help users easily navigate their work across Asana. So for example, on the screenshot here, you see we have the sidebar. The sidebar has rankings for projects, and this helps essentially users find projects easily, find projects that they're working on easily. We also personalize ranking for user face files across different work graph objects. So essentially, these user face files, as you can see on the top of the screenshot on your left, they help users understand who from their teams are working on a particular work content. And our ML experiences span beyond our main application. On the right, you can see email or a regular email that we send to users, and it has a prioritized list of tasks that we think they might want to work on. We also use ML to surface smart recommendations, so essentially helping users discover work that outside the work that they're already involved in. And we have personalized project recommendations and personalized team recommendations to help users find work that might be actually interesting to them. These recommendations have in particular been very useful for our new users in the onboarding flow, for example, as it helps us direct them to the right team, which eventually leads to more collaboration and engagement on the Asana platform. So I want to spend some time talking about the recommendation system that we've built. We'll deep dive into our modeling approach and then use that as a case study to talk about some of the learnings and takeaways that we've picked up along the way. So for those of you who are not familiar with the Asana interface, this is what a project looks like. These are fundamental part of the Asana Work Graph data model, and it helps users organize tasks relating to a particular initiative. And users are generally part of multiple projects, which they can navigate through different surfaces. For example, on the sidebar, this lists, for example, for this particular user, it lists all the projects that they're a member of. We ran some analysis and discovered that project memberships are directly correlated with users' collaboration and engagement on Asana. So in other words, more projects a user is part of, more engaged they were with the Asana platform, which led to better adoption and retention on Asana. Given these findings, we wanted to drive project membership, and we came up with the hypothesis that personalized recommendations is a way to do it. So we hypothesized that personalized recommendations can help users quickly find their relevant work, and this would eventually lead them to collaborate better on Asana, and this would lead to more adoption and retention on the platform. So with this hypothesis, we worked with our project managers and engineers to design a couple of surfaces to show recommendations, and these are two surfaces that we designed in particular. We added a widget on a user's home screen, so if this pointer works. Yeah, so this is a widget on the home screen that we added. Home screen is a central place for navigation for users, and we surfaced recommendations there. And we also added recommendations on users' inbox. So essentially, this was particularly for new users. So when a new user lands into Asana, this is one of the first notifications that they would see. So how did we figure out the best recommendations to surface to the users? Hint, hint, machine learning. We developed a machine learning model for this. We used the widely popular collaborative filtering approach to generate recommendations. And in particular, we used collaborative filtering that works on implicit data. Why implicit collaborative filtering? Because we did not have any external or explicit feedback from the users. That is, there was no rating or stars that a user gives to a project that they would to a typical movie recommendation system. Implicit collaborative filtering instead works on users' interaction data. So in our case, data points such as visits, engagement within projects like number of tasks that they've created, number of members that they've added, and so on and so forth. So with this data, for each organization that we have in Asana, we developed a user cross project matrix, where values in this matrix were essentially a measure of users' engagement for a given project, VIJ, which is. And this was essentially some weighted combinations of different interactions that a user can have with the project. So for example, we took a weighted combination of number of tasks that a user's created in the project, number of other users that they've added to the project, and so on. We feed the sparse matrix into a collaborative filtering model, which factorizes it. And then it fills in these missing values, which takes into account the preferences and collective behavior of all the other users, and hence collaborative filtering. And we rank these projects which previously had missing values based on what the final values were from this matrix factorization algorithm. Besides filling in these missing values, the collaborative filtering also gives us embeddings for the users and projects. So this chart here, it shows project embeddings. And essentially, projects that are similar to each other are grouped together in this two-dimensional space, and projects that are not so similar to each other are far off in this two-dimensional space. So for example, all projects related to sending people to Mars are all grouped together in red, and projects related to exploring Saturn are in green, all grouped together. So this is an interesting byproduct of collaborative filtering, and I'll be talking a bit more around how we use this for our purposes. Our model evaluation. How did we evaluate our models? So we ran both offline and online evaluation to figure out what the best model was. For offline tests, we used past data. So in particular, user project interactions and memberships. We considered multiple approaches for which model which models we should compare. So we compared our models with random baselines, with some heuristics, We tested out different hyperparameters, and then ran some metrics for some offline metrics like mean average precision, hit ratio, mean reciprocal rank to figure out what the best combination of hyperparameters and the modeling was. Offline evaluation obviously does not reflect true user behavior. So we ran A/B tests with the model that performed best offline. And our success metrics here for the A/B test was based on our hypothesis, which was to move retention and adoption among users by increasing project memberships and engagement. And we also use the same metrics that we used for offline evaluation, mean average precision at K, hit ratio as guardrail metrics. So we've talked about our hypothesis. We've talked about our final product, which was an ML-powered recommendation system. There was a bunch of key learnings that we picked along the way, from ideation to actually having a final product in Asana. And in the next few slides, I want to talk about some of the key insights and learnings. And I hope, our hope is that you can pick up some key insights to build better machine learning systems in your organizations. So one of the first things we did when we came up with our hypothesis was, and then the UI, was to figure out what is like a quick way to spin up like a recommendation system. It could be a basic naive recommendation system without going all in into the model. And to do that, we served some simple rule-based recommendations using a heuristic that could be easily computed with the infrastructure that we had without actually any complicated modeling or anything. So we used a popularity-based model where we just surfaced the most active projects in a domain to the given user. And using this approach, establishing a baseline and starting off with a heuristic had several advantages. So number one, this helped us establish a baseline. We were surfacing recommendations to the users for the very first time. And having a heuristic-powered recommendation provided us with a benchmark to start with. And the goal eventually was to improve on this benchmark that is created by the heuristics. Number two, it enhanced our understanding of the problem. So it helped us better understand our users and our users' reactions towards recommendation system. And this was key for us in understanding and actually building the model. So we drove feature selection, feature creation, model design through our learnings that we gathered from building a heuristic. And lastly, the heuristic ended up as a fallback mechanism. So in cases where the model failed to generate recommendations, this could be because there is not enough data available for a given user. Instead of showing an empty state, we still showed recommendations that were powered by the heuristic. So these might not be as good as the model, but these were better than just showing an empty state to the user. So the second thing that we learned along the way was the importance of building for different segments of users. So one of the key segments that we identified or that we analyzed in our data was how long a user has been using Asana for. We'll call it user age, not the demographic user age, but essentially the user's age on Asana. And we learned through our data analysis again was that new and existing users behave very differently to recommendations. For existing users on Asana, they were already generally member of projects that are pertinent to them, and surfacing new recommendations essentially increased visibility for other things that their team might be working on, but not necessarily surfacing work that might be directly related. For existing users for new users on the other hand, recommendations were much more leveraged. So since the users are just getting started on Asana, surfacing and directing them to relevant work and relevant projects was actually important in driving long-term engagement and adoption. We also had significantly different types of data available for new and existing users. So for existing users, we had their interactions and engagement with projects, but for new users, we did not have. So we could feed in the data that we had available for existing users into the collaborative filtering model, but again, for new users, we did not have that data. However, for new users, we had data around what projects or teams they were invited to. So in Asana, new users are generally invited to a project or a team by their teammate. And this data actually acted as like a good starting point for us. So instead of like to deal with this cold start problem of surfacing recommendations to new users, we just computed projects similar to a project that the user was invited to. So in the previous slides, if you remember, I showed a chart that showed like, we can compute similar projects based on the embeddings. We use that mechanism to surface recommendations to new users. So, oops, sorry. So now that we had set baselines, we had modeled for different users, the next step for us was to understand the impact of our model. And to do this, we wanted to run tests. But in order to run tests, we realized that it is important for us to isolate the impact of different components of our ML systems. So ML systems are complicated. They comprise of multiple components. For example, our project recommendations feature, we had a UI component, we had the production and machine learning infrastructure serving our model, and finally, we had the model. And given we built the model, our team, specifically our data science team, they were interested in figuring out what the impact of the model was, or how good the model was compared to like just the heuristic that we had spun up previously. So to do this, we ran 2 tests, sequential testing, one after the other. In the first test, we just changed the UI component, and another follow-up test where we tested by using this new UI component, which won in the first test, and then changing the model. So in the first test, we had like a new UI component that we introduced, and in the second test, given we knew that the UI component is good for our users, we kept the new UI component and updated the model. So instead of running sequential tests, you can also run multivariate tests, which is just like a longer version, which is essentially just like longer versions of like A/B tests. But pairwise computations or pairwise analysis in multivariate tests can also essentially help you achieve the same goal, which is to isolate the impact of different components and understand it. The last insight that I want to share before we talk about the infrastructure is the performance implications of serving machine learning. And this is a corollary from the previous insight, but systems performance, latency in particular, can have huge and sometimes undesired implications on ML performance. And I want to highlight this through one experience that we had, an experience that we built using the same project recommendations model. So Asana, because of its work graph data model, allows user to multi-home tasks in multiple projects. So what multi-homing means is that if a user realizes that a same task is relevant to 2 projects, they can add the same task in multiple projects. And we still give users suggestions for which other project they can multi-home a particular task to. And we wanted to update this ranking based on similar projects. So if a user has already added a project to a task, we want to surface other projects based on the similar project mechanism that I shared previously, around which other projects they can add that task to. So when we ran an A/B test, we learned, surprisingly, that our rankings led to a loss in some of the key metrics. We were pretty bullish about this, but this led to a loss. And after some digging, we realized that this was actually coming from introducing additional latency that we had added because of this experience. And how did we learn that? How did we figure out it was latency that was contributing to it? We ran a multivariate test where one of the variant was dark variant. And what I mean by dark variant is that in this particular variant, we read predictions from the machine learning system, but we do not surface those recommendations. So essentially, all the backend computations and everything that's happening to serve ML remain the same, but just that the ranking for the rankings that the user see does not change. When we compared dark variant with the ML variant, which essentially normalizes for latency, we found that there were positive metrics in the movement, but when we compared dark variant with the control, which essentially had the same UI experience and the same rankings, the dark variant performed worse, and this was because of the additional latency of running all the backend computations. So in other words, introducing latency because of serving ML led to an overall worse performance, even though our model was actually better than our existing rankings. So I want to summarize these 4 key learnings that we talked about before handing over to Zan to talk about productionization. But number one, start by establishing a baseline. This gives you quick learnings, and it also helps with model development and understanding of the user. Consider modeling for different user segments. Your model can have different implications, impact on different segments of users. So make sure that you understand potential biases or disparities in serving ML. Number 3 is isolate the impact of different components of ML systems. ML systems are complicated. Try to run multivariate or sequential tests if there are multiple things that you are changing in your ML system. And lastly, understand the performance implications of serving ML. Latency can have sometimes unintended impacts, so make sure that you're normalizing for latency or actually monitoring it while serving ML. So I am going to now hand it over to Zan to talk more about how we serve this using the infrastructure that we built.
Thank you, Sarang. So now that we've learned about the scientific and theoretical side of the ML, let's take a look at how we ship this from notebook into product. So we're going to start with an observation made back in the 1960s by Melvin Conway, which basically goes, organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. Or colloquially speaking, you ship your org chart. And we found that really applies here because the production infrastructure for running ML at scale falls under the ML team within the data infrastructure organization, which, as you can see, is noticeably smaller than the other orgs in our R&D division. We're not vertically integrated. We don't have a design or front-end development team, and we have to partner with other teams in the product organization to deliver our ML to customers. So our approach here would be to work together with cross-functional partners, such as the Foundations and Frameworks team, to compute, store, and vend the ML data to the product teams in a way that involves minimal integration effort and reduced responsibilities expected from others. So we also want machine learning to be a force multiplier within the large product org. So this incentivizes us to build models that serve multiple purposes in different parts of the product. For instance, the collaborating filtering model that was used for project recommendations also generates these byproduct data sets such as user similarity and the project similarity, and also similarity between projects and teams. And all of these are extracted from the embedding vectors that are constructed as part of collaborative filtering. So we find other places where we can apply these, such as surfacing similar people and projects that are similar to other projects. We've also built a notification priority model that can be broadly applied to different types of the work graph objects, such as tasks, comments, projects, and so on, because notifications are just links that are tying between these different work graph objects. And so these can be used both within the Asana application and in other channels like email and mobile push. So if we see directionally positive promise in deploying an existing model to a new surface area, even if it's not a perfect fit, it still either is a win that's shippable, or it is an indication that this is an area worth investing further in the future. Now, Asana takes customer trust and compliance very seriously. And every AI and ML use case goes through a review and approval process with stakeholders from legal, privacy, and security teams before implementation. Our in-house models are trained only with metadata. And so these are what comes from connectivity within the work graph and telemetry from logs. No user work content, things that were actually input as text by the user, is used for training these models. And so we provide a set of admin controls to customers so that they can decide what scope that AI ML product features should be allowed to run within their domain. This allows you to exercise separate controls for our in-house metadata-based models versus the other ones that we developed, other product features that we developed in partnership with external vendors such as OpenAI and Anthropic. And so in order to take all of these preferences into account, we built an eligibility framework that ensures and applies these controls as a gating process, both in the ML processing and the customization of the product experience. Now, the product use case itself will also dictate the mode of operation needed for each ML model. For use cases in, say, navigation and recommendations, it made more sense to do batch processing because they were resource and data intensive. And customers would also be less surprised if the results remain consistent over time. However, for use cases that were centered around prioritization, it was more important to use fresh, time-sensitive input data and maintain a short feedback loop so that in those cases, we would have to do real-time on-demand inference. So now that we've explored what we need to accomplish here, we can kind of arrive at a strategy for looking out from the status quo of what we already have in our data platform and determine how we would sequence our upcoming infrastructure investments. In the earlier phases of the platform maturity, we have more pre-existing data infrastructure, particularly the stuff that was already in place to support data analytics. So these are things like offline data acquisition, exporting from the Work Graph data model into a data lake, batch processing pipelines. We already had this available when we were building our first ML experience. And so as we move on, we look into building out data vending and inference serving solutions to deliver the ML product. These require a few more components to be spun up by the ML infrastructure team. And so further along, we adopted the Databricks feature store while our ML efforts were already underway. And the biggest benefits there are in the collaboration and discoverability on feature engineering and the easy publication of offline computed features into an online feature store for model serving. As the platform matures, we invest more in improving the observability, maintenance, governance of ML models, and further optimize the development process and ML ops ergonomics. So let's take a closer look at this batch pipeline that we have for recommendations. As mentioned, we have the data that we've exported from our Work Graph into Data Lake. That's our data source. We have transformations that compute features that are used to construct the training set that is used for recommendations. Training process fits a model to this data set using industry standard tools, and then that model is used to generate batch inference. It's fairly typical. However, the collaborative filtering approach applies only to one customer domain at a time, and each one has to be walled off from all of the others for relevance and privacy reasons. And so we need to operate this in a multi-tenant mode over 100,000 times per day. And so how do we solve this? Well, since you're here at Data AI Summit, unsurprisingly, the solution is something we have available in PySpark. Now, as we hinted earlier, our staff has a high degree of specialization. So many of our data science team members have familiarity with typical tools of the trade, almost universally surrounded based on pandas. And they've been able to explore and prototype with those tools in their Databricks notebook environments. But they haven't had to operate them at a large scale. Fortunately, PySpark offers us a very gentle on-ramp for these existing pandas-based code paths to be parallelized at production scale. And so we have these two different functions that can operate on data frames. You have, on the left there, you have map in pandas, which can take a pre-trained model and apply that efficiently parallelized to a large data set row by row. And then the second one I have here on the right is apply in pandas. And what that does is it actually partitions your data set by some kind of group key. In our case, we would use the customer domain ID so that then in parallel, we have separate recommendation models being fit to each data set, and we execute 100,000 or more of these per day. And so finally, we join those all together into a output data set that we can materialize. Now, I said materialize. It has to go somewhere that is accessible by product. Product is not going to talk to a data lake. It needs to be vended through a system that has the ability to support both high throughput bulk data ingestion, because we're going to generate a massive amount of data with a big write spike every day, and also low latency and high concurrency retrieval, because the product is going to be fetching 1 or 2 records at a time, typically. So our foundations team, as I mentioned earlier, is in this picture, but they are very protective of the customer experience and system availability for the storage infrastructure. And so this batch ML case introduces a new usage pattern that we have to be a little careful around. And it motivated us to set up a separate storage and vending solution. We still wanted durability and fault tolerance, but we also wanted an easy way of deleting old records and so that we could satisfy compliance and control the storage footprint. And this is actually becoming more and more important in a world where holding on to data longer than necessary is actually considered a liability. And we found that a managed distributed key value store happened to be like the sweet spot for this kind of solution. We use DynamoDB because we are an AWS cloud and we have internal expertise in operating it, but others in this space can probably solve the problem equally well. We did also consider using an in-memory data store like Elasticache for Redis. There is a crossover point where that does become advantageous, and that's usually where the I/O saturation from refreshing the same set of data over and over again takes precedence over the cost of scaling out storage horizontally. In our analysis, we did not reach that kind of scale, and so our solution based on Dynamo was significantly less costly. And finally, coming back to an earlier topic, we do also have a set of models, mostly around prioritization, that require on-demand evaluation. And this is because they require source of truth inputs representing the state of the world at the exact time of evaluation. And for these, we found that SageMaker multi-model endpoints were a great solution for our needs. The new models that our data scientists would train can be obtained from their Databricks notebooks, and deployment would be as simple as just dropping a model artifact onto an S3 in which that endpoint will be able to start serving it immediately. The clients are still going to be responsible for assembling the feature vectors that they have to supply as input for the model service to evaluate. But some of those features are a bit difficult to compute. For instance, features that are based on log data or historical aggregations. And so this is where the feature store, once again, comes in handy, because those can be pre-computed and vended here. The Databricks feature store made it very easy for us to maintain an offline feature store and easily import the existing Delta Lake tables that we had, cataloging them for discoverability and collaboration. It also allowed us to selectively publish features to the online feature store so that we only need to vend the values needed for the real-time models, and the others are just kept around for reference for future model development. And so this also helps us save cost. There's also side benefits that come with making it easier to trace the data lineage and maintaining an audit trail for troubleshooting. So in summary, I would say our key learnings are that, first, it's important to understand the cross-functional requirements beyond just executing ML. The solution landscape takes into account many different stakeholders, but we can also leverage internal expertise. The data volumes and the product needs will determine the ML serving solution, whether it's batch or on-demand or real-time. It's also helpful to find a balance between incremental and iterative development. And by that, I mean that ML components at all different positions on the platform can be adopted selectively and in strategic phases. And so when you go very wide and adopt more of those components, you can increase your supported scope in the short term. But if you go very deep in optimizing one type of model deployment, then that will increase your release velocity with similar use cases there. Finally, Pandas on PySpark, it's awesome, makes things very easy to scale up and deploy to production. So I would like to close with a shout out to all the contributors from both our team, our partners, and those who develop the underlying platforms and tools. Thank you.